of Unit 5. What we'd like to do is go through these 7 points that you see here on the left, okay, in your math notebook. So go ahead, open up your math notebook, and for each question, write these titles so that you know how to identify those skills. We're going to look at equivalent fractions, okay, equivalent fractions, or making more equivalent fractions, converting improper fractions to mixed numbers, converting diagrams to fractions and mixed numbers. By diagrams, we mean like if a square equals a whole, what is a square and half a square equal as a fraction or mixed number. Adding fractions with fraction sticks, using the fraction sticks to add fractions like 1 over 8 plus 3 over 8 equals, so on. Comparing fractions, which fraction is greater than the other. Estimating circle graphs, we will look at an entire circle graph and we'll try to identify the percents and fractions. Estimating circle graph, we did that, using percentage to identify data. If I tell you what is 20% of 1,000, you have to be able to tell me it's 200, right? 20% of 1,000 is 200. Or what is half of 1,000? 500. Okay, let's go ahead and write the title, Written Assessment Review, Unit 5. And let's start with number 1. Go ahead for number 1 and write the title, Equivalent Fractions, and write these 3 fractions, 1a, 4/9, b, 18 over 24, and c, 4/5. Okay, and write 3 equivalent fractions. Pause the video now, solve it, and we'll check the answer after you've completed them. Okay, for a, we can go ahead and take and double them. If we double both, whatever you do to the top, you must do to the bottom. Okay? We double them. We know that we can have 8, right, over 18. That's an equivalent fraction. I can double that again and have 16, right, over 36. And I can double that one more time as well and have 32 over 72. And that right there, boys and girls, are 3 equivalent fractions. 3 equivalent fractions for 4/9. Okay, let's do 18 over 24. In order to find equivalent fractions for 18 over 24, we can find a common factor. We know that they're both divisible because they're both even, they're both divisible by 2. So you can divide them both by 2, and that'll give you an equivalent fraction. If you divide the top by 2, and you divide the bottom by 2, you're going to have 9 over 12. Right? You can also see that they're both divisible by 3. Okay? The divisibility rule for 3 is that if you add both numbers, whatever number you get, or the sum of both numbers, must be divisible by 3. So here you get 9. 1 plus 8 is 9. That's divisible by 3. And 2 plus 4 is 6, which is also divisible by 3. So you divide them both by 3, and when you do that, 18 divided by 3 is 6, and 24 divided by 3 is 8. Okay? You could simplify this one, okay? And you notice that over here you have, they're both divisible by 2. So here you have a 3, and here you have a 4. And it's actually 3/4. It's the simplest form. And there you have 3 more equivalent fractions. And now let's try 4/5. Okay, whatever you do to the top, you must do it to the bottom. So let's say we double it, or we quadruple it, or anything. Let's say we double it, times 2, and this times 2, right? 4 times 2 is 8, 10 times 2, 5 times 2 is 10. There's 1 equivalent fraction. Okay, you can go ahead and do the rest as you can see. Okay, let's say if you double this one more time, 8 times 2 is 16, and you double the bottom, 10 times 2 is 20, and you can double it one more time, and you have 32 and 40. Okay, boys and girls, these are all equivalent fractions. They all mean the same thing. They all have the same value. Let's move on to converting improper fractions to mixed numbers. Go ahead and write number 2 A, B, and C. We have 31 over 9, 13 over 5, and 22 over 18. And we're supposed to now convert these into a mixed number. Remember that these are improper fractions. No answer should be left in this format. It is wrong. We need to change it into simply a mixed number. The way we do so, boys and girls, is we need to see how many 9s we have in 31. So you're really dividing 31 divided by 9. And we know there's going to be a remainder. Okay? So we have to count how many 9s are in 31. We can start by counting by 9s. We have 9, 18, 27, right? And then if I count one more, it will be 36. That goes over 31. So it's 9, 18, 27, and then stop there. So there's 3. So far there are 3, right? So there's 3 of them. And what do I have left over? What do I have left from 27 to 31? We have 4 left over, and then we just keep our remainder right here, which is 4, because we really only have 4 out of 9 left, right? 4 out of 9. And there you have it. Okay, go ahead and continue with that. How many 5s do we have in 13? How many 5s do we have in 13? Oh, by the way, if you did not pause it after you wrote these down to wait for the answers, or to solve it on your own, please pause it now. Remember, you're only hurting yourself if you don't try these by yourself first. So go ahead and try B and C alone. Pause the video if you haven't done so. Okay? Continuing. How many 5s are in 13? Well, let's count. 5, 10, 15. Oh, 15 goes over 13, so there's really only 5, 10. There's 2 of them. There we go. What do I have left over? Okay, I have 10, so I need to get 13. I have 3 left over. 3 over 5. Okay. And now 22 over 18. How many 18s do we find in 22? How many 18s can fit in 22? Well, only 1, because if I count by 18s, I have 18. The next one is 36. That's way over 22. So we really only have 1 18. So you go ahead and write the 1. And then what do we have left over? Okay, we have 4 left over, because from 18 to 22 is 4 over 18. Now, take a look at this. 1 and 4 18s. Am I done? Many of you are saying no, because I still have to reduce the fraction. So we reduce it so that I have 1, okay? And they can both be divisible by 2. So I have, divide the top by 2. So you get 2, and you divide the bottom by 2, so that you get 9. So it's 1 and 2 9s. Let's move on to converting diagrams to fractions and mixed numbers. When we talk about converting diagrams, when we say the word diagrams, we really mean shapes, like polygons, okay? Over here, this is a hole. That's what we're going to call it this time. This is equal to 1. Well, here's your first question. Okay? Oh, well, not yet. Let's just make this the example. Okay, this is the example. How many do we have here? Well, we notice that we have 3 equals 1 whole. Okay, so we have 1 right there, 2, and then 2 out of what? Well, we need 3 to make a whole, so it's 2 out of 3. So 1, 2, and 2/3. So it's 2 and 2/3. Okay, let's try some questions. Go ahead and write down 3A, B, and C and draw these figures. Hexagon equals 1. So here's one hexagon, here's another hexagon. Okay, some hexagons here have been cut in halves. Here's a full hexagon that's been cut into thirds. Okay, hexagons complete. These are half of hexagons. And here, there's one that's been cut into 6. You can see that you could probably fit 2 more pieces there. Okay, pause the video, solve the 3, and we will check our answer. Go ahead and pause. So, if one hexagon is 1 hexagon, means 6 sides, equals 1, we have 1, 2, and this is only a half of a hexagon, so we have 2 and then a half. 1 part of 2 parts. You see, 1 part of 2 parts. Only one of 2. Okay, continuing. B. I forgot my equal sign. B. Okay, when we count, we have a half plus a half is a whole. So there's a whole, right? Plus another whole, right? So we have 2 at least. Then we have a half, don't we? And then we have 2/3. So a half plus 2/3. That's going to give us one more, won't it? But another way to solve it, boys and girls, let's make this a little bit bigger so I can explain it. We're going to take the smallest unit that we see here, the smallest fraction, and it's this one, right? We've taken a rhombus or parallelogram, a rhombus, and cut it into 2, and that is the smallest. Okay? And we know that we have 3 rhombus in a whole, don't we? Because the hexagon is the whole, and here we have 1, 2, 3. But the rhombus has also been cut in half. So in reality, we could have 6. So we could cut that into 6. Just like that. So a whole could also be out of 6. Right? So why don't we make our whole out of 6? It's out of 6. Right? That's our denominator. Because you can fit up to 6 pieces, 1, 2, 3, 4, 5, 6, in one hexagon, a whole. So our whole can be cut up to 6. Well, how many of these pieces do we have here? That's simple to check. 1, 2, 3. 1, 2, 3. 1, 2, 3. So now let's count them all. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 over 6. But we all know this is an improper fraction and we cannot leave it like that. So change your improper fraction to a mixed number. We did that already before, right? We did that in number 2. How many 6s do we have in 17? Well, if we count by 6s, we have 6, 12, 18. 18 goes over. So 6, 12, that means we only have 2. And then what do I have left from 12 to 17? I have 5 left over 6 to have almost a third. If this were 6 over 6, we'd have 3, which would mean this would have to be 18. The 17 would have to be 18. Okay, and there you have it, boys and girls. Use the same method to solve the bottom one. You know that we have 6 little triangles inside a hexagon. 6 triangles inside a hexagon. We have 3 in the halves, and over here we have 4. So our denominator is going to be 6, and then how many triangles do we have in total? As we did before, go ahead and cut them out. You know that you have 3 here, 1, 2, 3, and 3 here, right? You see them? And then over here we have 6. Just connect all the little corners and you get your 6. And we know that our maximum in a whole is 6. Correct? There's our whole, and our whole has been cut into 6. So we make that our bottom number, 6. And now let's count the triangles. 6 plus 3 is 9, plus 3 is 12, 13, 14, 15, 16. Okay? So we have 16. How many 6s are in 16? If you said 2, you're correct. That leaves us with 4 over 6. But this is not complete because you have to simplify the fraction. So it's 2 and 2/3. And there's your answer, boys and girls. 2 and 2/3. Alright, let's move on to adding fractions with fraction sticks. Adding fractions with fraction sticks.